Okay, a couple of things we want to go through while we're learning assembly is system calls, which are used to do basic input and output. These are simulated calls inside of the QT simulator. They would work differently in a real operating system, but for this simulator, you need a couple of things to make that pretty much will help you out. They're like operating system calls. You have to set up the return address, if you're having one, with V, or return argument, to return the function, and then any arguments you need to put through your register. This is if you want to print an integer, like what's stored in a register. You want to print a string somewhere, or maybe you want to read an integer from input. And those are the big three that we're going to be using. And there's plenty of others. You can print a float, a string, an integer. You can read a double or read a string. I wonder what SBRK stands for. I don't care. Exit terminates the simulator. Are we getting no examples of this? Oh, this is so terrible. All right.
No slides today.
Yeah, the slides are failing me today. All right, let's look at what the syscall looks like.
I think you actually need to remake them.
Yeah, they're going to be all remade. Sadness. All right, what's being stored in data?
Value.
And MSGL.
String.
That's a 1.
3 words is a message.
Thank you. First is being stored 3 words. That each of those 3 will contain the value 0. Next comes a null terminating ASCII string, because that's what the Z stands for, null terminating. Always use ASCII Z, otherwise sadness.
ASCII Z.
So you're going to have characters SUM space equals space and then \n will come afterwards. Yes.
If I want to write my code for readability, you got value here, you got word, word, word. What happens if I say, okay, I want this to be value 1, word 0, value 2, whatever.
You could do that,
create
yeah.
multiple labels.
Oh, yeah.
Label, and then so I can say, well, I'm getting the temperature here, the pressure here.
Yeah, you can do. Sure. And then you get it's just labeled Superman. I'm just showing you can do whatever you want.
Why would you call it Superman?
Exactly my point.
Batman's the...
That is true. Batman is better.
It's freaking getting this way.
Personally,
Yep,
I like
there we
Marvel
go.
better.
The door is over there.
I know where the door is.
I just like
located.
movies.
Okay.
All
I
right.
was-
I don't
Load
care about
value, which is the first address of that word. We're going to load the value 5 as a syscall. We're going to do a system call for read int. Right, we set up 5 to tell it what system call it's going to be. We store, we do the system call for read int, and that is going to store the integer we get back into v0. v0, we're then going to take whatever that was and store it into the first memory address, namely this guy right up here from T0. What? Okay. Are we good with this instruction?
Yeah.
Okay, good.
That one's good.
Load immediately. We're going to put 5 into the register V0.
I just made up 5.
5 is the code for read int.
Oh, you use numbers. Okay.
Right. Because words would be way too complicated.
Words would take too long.
Yeah. That's telling us when we do a system call instruction that we're calling read int. By the way read int works, it's going to return the integer we get back into V0, so we're going to store that out into basically this value right up there. We're going to call read int again and get the value and store it into the second word right up here. We're going to then load both those words, add them, and store them to the third. Then, so what is the third one? Okay, so the third one's going to have the sum of the 2 numbers we entered. Load I, or load immediate. 4 is system call for print string. We're going to load, oh, it's getting tiring saying all this. Address of MSG1, aka where this sum equals begins, into A0, do the system call. Since it is a print string, it's going to print what's out there. Next, we're going to tell it to do a print int, load the value t0 into the first argument, do the system call, and then jump. So what is this program doing?
Adding stuff.
Adding what?
The
The first and the second word to the
Of-
and then of the
Of what we get back from the system calls.
yeah.
All right. So
Then
let's
we print
let's
it
see
out.
what QTSpim does with this. There was changes.
oh,
Not
it's
happening.
you.
Oh, because of Superman.
Ah.
He always gets you. Right?
Great.
Okay, so let's watch this. All right, the main gets set up. Hopefully main makes more sense now of what's going on because it's setting up the function call. So load value, again, just for emphasis, value is, where is value?
The third one. No.
Yeah, it should be this one. Yeah, it's going to be that one. Hey, look, the assembler rearranged the memory. So it's going to be up here. 10, there it is. Then we're going to stuff 5 into register 2. Register 2 is V0. So we put that in there. It's now 5, which is read integer. We do the system call. It pops up the console. All right. When you do this console, be very careful because if you end up typing 50 and you want to do a backspace, it'll break everything. Because if I hit enter, sadness has just occurred. It doesn't know what's going on. So I need to actually stop the simulator.
Oh, so be
re-
very careful when
Right.
you're.
I'm just telling you, bad things will happen. So I'm back to where we were doing the system call again. And I'm going to put in 50. All right. Comes back from the system call. We're going to store that register 8, which is where the memory address was. So I'm going to hit F10. And there it is, 32. Or putting 5 in again. Great. Doing the system call. Give me another number.
26.
26. Store what came back into the next element. So that was 32, 20, well, 50 actually. And then this will be, was it 1A? All right, great. Now we're going to load those two values into T1 and T2. So there's T1, T2. Let me do those two real quick. We're going to add them, put them into T3. And then we're going to store that back out into data. Where'd it go? Should have been
It's
right
the
there.
first part. And
Oh yeah, it put it back at the beginning. Thank you. So it actually updated this one right here. Now set up the system call for a print screen. That's 4. Put the argument for MSG1 into argument 1. So wait, yeah, there it is. That's the return. Yeah. Are we doing the system call yet? Here's the system call. Now you do a system call, so sum equals. And now we're going to do a, for integers, so that's what $1 or 1 is. Again, print int is a 1. We need to update A0 to 4C, which is the answer, and then you do system call equals 76. Then you come back from main, no op, do the final system call to exit, and you're done. All right.
This
Yeah.
seems
Go
a
back
very
to C++.
complicated way to add two numbers.
Can we go back to C++?
Does the system call automatically save the register address as part of the function?
The system call is going to preserve everything but your temporaries, your V, and your A registers. Seems complicated, but remember, we're coming from our single cycle. Remember our single cycle processor? That's what we have. How can we use that to do printing and whatnot? Well, here's one way to do it. This is actually one of the better ways to do it. Trust me. Can we all, now you see how much work C is doing for you?
I like it.
Isn't C the best?
We're supposed to make the computer do our work for us.
Right, I agree.
We're lazy.
Mm-hmm.
We're very lazy too.
Big juice box.
Not a juice box.
Juice
Okay.
bag. It's a juice bag.
It's a pouch.
Pouch.
All right, let's go ahead and go through. I'm going to do a couple more examples with code. You have all this code, but I'm going to go ahead and basically just showcase it.
Yeah, punches you in the face.
No,
Okay.
It's French punch.
The fruit punches you in the face.
I have two pieces of data up here, string for ASCII. One says equal, the other says not equal. Hint, hint, what's going on.
Whoa.
We're going to read an integer, store it into temporary 0. Read another integer, store it into temporary 1. If the two are equal, we're going to jump to the equal label, which is down here. So if it's the equal label, we jump here. We load the system call for a print string. We load the address for the equal message, and we print the equal message, which says it's equal. Then we have a label here. Will make more sense in a minute, and then we exit. So that's if the two numbers are equal. If they are not equal, then it's not going to jump here. It's instead going to move on to my net not equal label.
Whoa.
Load the print string, and put the address for the not equal message in there. Do the system call for not equal, and then jump to the after equal label test, which is down here, thereby skipping the equal message. Okay? All right.
Whoa.
Magic.
Magic me.
I don't know why I did that.
Computers are magic.
Computers are magic. In a way. All right, we're just going to run it. All right, two numbers, 55 and 43. Not equal. Who would have guessed? I know. Whoa.
So you can choose binary hex.
Oh, if you accidentally close the console, you have to do this to get it back. Equal. Yay!
Whoa.
Any other questions?
I assume we're not going to do anything super crazy complex in assembly.
All right, now to recursion.
I could go.
You can dream, but
Oh yeah, let's do the QTSpim of recursion just to see what it's doing first. We're gonna run. We'll put in 5 factorial. 5 is 120. Unfortunately, there's no easy reset. You have to do reinitialize and load file. Yes, I know that's annoying.
Can't you just do the shift?
Nope. And when you do that, sadness. Oh, 70. It took it that time. Is 0. Probably because we overloaded the stack. We'll get to that. Oh, I did template. That's not good. What's the go button on this one? F5. And let's do 3. Okay, you get the idea of what it's doing? Just printing off the factorial. Great. Whoa. All right, how do we do that with recursion? Oh.
With code.
Actually, we didn't do a loop, did we? Okay, we'll do recursion first then.
Oh wait, did we do?
No, we didn't do
Oh,
a
we
loop.
did a branch.
We did a branch, but we didn't go to
Go
looping.
back.
We'll do loop. We'll do recursion first. This is just so you can print off factorial with the equals afterwards. You're happy about this step. That's great. Oh, I'm glad. I'm glad. You gotta go through this, and then now you know why we don't do this again. No one codes this way.
Oh, so basically we're learning why we
Why we
our
don't
others.
We're
use
gonna
it.
have a lab just to get it out of the way, and then we're not gonna.
Yes, but now you have the experience doing it, so when you have errors that have to come up with assembly, like, I don't know, Meltdown Inspector, you'll know why, you'll know more of what's going on, right?
I'll say, just let it happen.
essentially what happened.
It knows what it's doing.
We're just gonna let this go, all right?
I'm sure nothing bad will come from it. No big deal.
Wow. All right, load up a read integer, do the system call, move that into temporary 0. Okay, great. Now we're gonna do the function call to factorial. Oh boy.
Oh boy.
Edit the stack pointer, store the return address into the stack pointer so that we know where we're going back from main. We're moving the value from temporary 0 over to argument A. There we go. Jump and link factorial to make the system call. Notice afterwards we restore the return address, fix the stack pointer, and then, we move that one to V0 so we can print the results afterwards. But let's get to that in a moment. Because right now we're actually jumping from factorial, we're jumping and linking to factorial. Okay. Let's see, branch if less than, namely, if the value in there is less than 2, then that means we are done, because we know what the factorial of 2 is, don't we?
2.
Whoa. All right, good. Magic. So let's see, branch if less than 2, it's 1 in that case, in which case we'll return 1.
Oh.
Namely, we store 1 as the return, and we get out of here. All right. Hey, what is that? That is the
Answer.
what?
Answer.
For when I tell you to do recursion, I tell you to first do your
Oh,
Base
base
case.
case.
base case. So that's your base case. Once the value is less than 2, we're just going to return the value 1. All right, not exactly correct for 0, but we're just going to live with it for now. Otherwise, code starts getting messy. Let's say it's something higher, like, I don't know, 5. Well, we need to first call the factorial of 4, right? So we need to set that up. We're going to increase the stack pointer by 8 bytes because we want to store the return address and our argument that we had, which was 5 coming in. So notice, ooh, I get to draw on the board. Yes! You're going to have some memory address and the value 5. We're going to subtract from that argument, so 5 would become 4. Actually, I should store this over here. Sign A0, which is 5. We're going to subtract 1. Don't worry, online people, I'll show you in a minute, which will make it 4. And now we're going to jump and link to factorial, aka we're calling ourselves, which would put us back up here. Okay, y'all see the code?
Yeah.
Let's jump over to the board for online people. So we're calling it with 4. Is 4 less than 2?
No.
No. So what are we going to do?
Keep going.
We're going to call ourselves.
Yeah.
So again, we need to store our new memory address, whatever that was, the value 4 as well, and then call ourselves. Well, we got to store another memory address, the value, and then call as well, and then here it's just going to continue. 2, call as well, and then finally we're going to put 1. We're going to do a call with 1. I'm sorry. I haven't been updating A. Because it'd be 4, 3, getting too excited, 2, and then 1. Now when we call ourselves and the value is 1, what are we returning? 1.
1.
Then $V0 will equal to 1. So the stack looks something like this if we had 5. When we finally, over in our code, A is 1. So that means we're going to load the answer 1 into V0 and then do a jump to return, which means we're now back to this line of code, and our current stack is pointing to right here. We're going to restore our 2 variables, the return address and A, was it A0? A, which is this guy, so then A0 will then become 2. A. We're going to then manipulate the stack pointer. So the stack pointer, instead of pointing there, will now go up to here, because we no longer need that memory, because that's what we used when we did the function call, so we automatically deallocated that. We do the multiply. V0 and A0. 1 times 2 is 2. All right. Sorry, people online. 1 times 2 is 2. Great. Jump factorial return, where we just return from our previous call. And that's going to put us back up to here with a call at this point in the stack. So the first thing we do is we update our return address and we load the new value to the stack pointer. All right, whoops. Update the return address with that value, so RA has whatever's up there, just putting that there. A0 is going to be restored to 3, and then we're going to update the stack pointer so it does go up to here. Ooh, this is getting a little messy, so I'm going to write V0 over here. We had it at 1, then it became 2. All right. Let's see, update the stack pointer. Now we're going to do the multiplication of V0 and A0. So A0 is 3, V0 is 2, so that would give us 6. Jump to the return, which is going to return from our address and eventually put us back up here from our previous call. So we're doing the jump from here. It's going to put us back, back to our call. First thing we do is we restore the return address of this value. We then restore A0 to be 4. So then the stack pointer gets updated again to here. We'll put a line right here, so that makes a little more sense. Update the stack pointer, do the multiplication, and then return. Okay, so what is 4 times 6?
24.
All right. And we're going to call ourselves again. I'm just going to show it now. We call ourselves again. We're going to look at these two. Update A0 to be this value that we stored, which was 5. Update the stack pointer. Well, you update the return address to that one. Stack pointer's back up here. Then you multiply 5 times 24, which is 120. And then we finally get out a factorial, which is going to jump us back to main. Which is right here where we did our initial jump and link to factorial.
Wow.
Reload the return address from main so we know how to exit. Decrement the stack pointer. Move it into V0 because what's going to happen next is I'm going to do first a print of that first string, factorial sub, print the integer 5 or whatever came in from standard in, print the end of, in parentheses equals, and then print that final integer that we got back from our function call. Okay? Do y'all want me to step through it in QTSpim, or are you good with the example or the way I did it manually on the board?
I think we're good.
That's fine.
I think we're good.
John? Good? Kalia? Okay, great.
What did you say?
I think we're good.
These slides are looking in the,
If they're not, tell me and I'll make sure they're up there. The code is. All right, last one is summation, or not summation, looping. Let's first look at what this one does. Boop, boop, boop. Simulator. Run. 5. 5 plus 4 plus 3 plus 2 plus 1.
Oh, it's the same thing, but with addition.
Addition, and we're using a loop.
Oh. Okay.
So let's go look at that real quick. Sum equals, right. System call for read int, so we're getting an integer storing to T0. We're going to load T1 as our counter, T2 is our sum. Actually, this one looks really good inside QTSpim, I remember. You're going to add 1 to T0. Then add that T1 over to T2, which is our sum. Branch if T1 is back to 0, namely we're done. Branch if not equal, sorry.
What does that mean? Branch if not equal?
Branch if not equal, so if these two are not equal to each other, branch up to the top.
So do it again.
Yeah, here, let's do it through QTSpim, that'll make a little more sense. All right, let's get this going, set up main. System call for read int, let's go ahead and read in 5. We're going to get that value from 5 stored into T0. There's T0 with 5. We're going to set up our counter. That's I. So T1 is going to be I, for int I equals 0 up to whatever we just put in. T2 is going to be the summation variable, int sum, started at 0. Next, add 1 to I, and then store that into T2, which is our sum. Now, if branch if not equal, let's see, $9, which is this guy, and $8. Once I has become 5, we want to stop. But it's not 5 yet, so we're going to jump up 2 instructions.
So
Or 8, yeah, 2 instructions, yes.
P and E is like while not equal.
Right.
Keep looping.
Yeah, you got it. So we're going to add to I again. I becomes 2, or T1 becomes 2. We add that to sum. T2 becomes 3. They're not equal, so we jump up again. We add it again, so I is 3. We add that to our sum. That's 6. They're not equal. Jump up again. Add 1 to I, so it becomes 4. Add that to our sum, which becomes 10. They're still not equal. Jump up. I becomes 5. Add that to our sum, which gets F, aka 15. They are equal, so we don't branch. And then we set up the system call for printing out the message. Do the system call, sum equals. Set up the system call for printing the integer, equals 15. We return from main, and that causes the exit system call, and we're done. How's that? Okay.
In that T2 register, it was counting, and so it went 1, 3, 6, and then when it got to 10, it changed to A. Is that because 10 is A in
Hex.
hexadecimal?
Yes.
Yeah, I'm gonna have to remember all that.
Yeah.
I know it seems confusing, but it's way easier to read hex when you're dealing with pointers than to try and do them in decimal format, because decimal makes no sense with pointers. Okay.
As long as we're not doing it in binary.
Exactly. All right. I think that's it. Yeah. Any questions before we do the lab?
No questions after that.
All right.